Okay, so far we have completed up to chapter 5, and in chapter 5 we have studied the gas laws and laws of partial pressures and intermolecular forces, etc. Right? Those very important and very nice chapter we have finished in chapter 5. Now let's go to the chapter 6, and in which we will also study the very nice wonderful properties of the solutions and the colloids. We will study that. So let's go. So first of all, let's remember the types of the solutions. Okay, so we will study the different types of the solutions, like the saturated solution, unsaturated solution, like that. Okay, but before that, let's know what is the solvent. Because if you mix two, if that is a homogeneous mixture, one is solvent and one other is the solute, right? Solvent, generally the fraction of the solute in which the other components are dissolved. And the solute, a substance that is dissolved in a solvent to produce a solution. So that's the solute. For example, if you have a sodium chloride solution, then the sodium chloride is a solute and the water is a solution. Water is the solvent. Okay. So generally, which is abundant, which is a larger quantity in the amount in the mixture, that can be considered as the solvent, and which is a smaller quantity, that is the solute, right? So that's why eventually water solution of sodium chloride, then the sodium chloride is the solute and the water is the solvent. So now let's see most common type of the solutions. So gas liquid solution, we can have gas plus liquid. For example, carbonated water, that is the gas liquid solution, right? And the liquid solution we can have, for example, wine, water and alcohol, right? Liquid solution. And solid liquid solution, that is the salt water, right? And this is the solution also the liquid. And the gas solution, for example, air, right? Guys, air is also a solution. That is the gaseous form of the solution. And the solid solution, for example, alloys, right? 14 karat gold, 18 karat gold, alloys, brass, for example. These are the solid solutions. Okay. Alloys also can be taken as a solution if they are homogeneously mixed. So solutions are not only the liquid. Some solutions are liquid, some are solid, some are gas. So phase of the solution can be any. Okay, phase of the solution can be any. And for example, if you dissolve the sodium chloride in water and freeze it, that is also a solution, but that's solid, that ice, salty ice. So you can guess, right? The ice, sugary ice, like the ice cream, right? That's the solid form, right? But this is the solution. Okay. So popsicle, for example, that's a solid solution. So solution can be liquid, solution can be gas, solution can be solid, and there are some examples. Okay. So in case of the gas liquid solution, the form is the liquid carbonated water, carbon dioxide is the solute, and the water is the liquid. That's why gas is the solute and the liquid is the solvent. So if you see that, what is the phase of the solvent is the phase of the solution. Phase of the solvent is the phase of the solutions generally. Okay. So phase of the solvent, now we will write down here. Okay, phase of the, generally the phase of solvent is generally, so that generally happens. Now these are the different type of the solutions. Now let's think about the characteristics of the solutions. What are the property of the solution? So the distribution of particle in a solution is uniform. This means the homogeneous mixture. So it's the uniform distribution. So what does it mean? So uniform distribution means like this. Okay. So uniform distribution. So distribution of the So distribution is uniform. This means that, so this means the distribution of particle is uniform. What does it mean? For example, let's say this is one beaker and it has a solution, and this is solution. This is up to here, this point we have solution, right? Let's say these are the solute particles in the solution. They uniformly distributed. What does the uniformly distributed means? Take 1 spoon and 1 spoon solution from here, and if you see that solution and you find that 5 solute particle and 100 solvent particle, for example. That's just the example, okay? So, and you take 1 spoon from here, that also will have the same. If you take the spoon from here, that also will be the same. So for example, 1 drop from right now, for example, you take the solution drop wise. First drop has, for example, 5 molar concentration of the sodium chloride. Suppose this is the solution. Second drop also will have the same. Third drop also will have the same. Fourth drop also will have the same, if this is the solution. So because it is the uniform distribution, means that the density at every part. So if you take the sample, every sample has the same density. Every sample has the same molar ratios. Okay. Every sample has the same volume, exactly same volume. First sample, take 1 spoon. If it has, for example, 10 mole, 10 ml. Then second has also 10 ml. Third has also 10. So volume same, density same. So every sample has the same density, same volume, same chemical properties. For example, if it is the acid solution, so first drop has pH 5, second drop will have also pH 5. So all the properties, the heat transfer properties, vibrational properties, right, and physical properties, chemical properties, all the properties will be uniformly distributed if that is the solution. And the concentration is also the same. So first drop has also same concentration. What is the concentration you get from the first spoon? Second spoon is also the same. Third spoon at the end of the point also the same. So that is the one property. So component of the solution do not separate on standing. That is another. The solution cannot be separated into components by filtration. That is another property. So if it is not the solution, you can filter it and you can separate it. You can centrifuge it and you can separate it, if that is not the solution. But the solutions means that the particles are they live together by the intermolecular forces. So that the solution has the intermolecular forces. Because of the intermolecular forces, the distribution is the uniform there. That's why you cannot separate that with the filtration. Okay. For any given solvent solute combination, it is possible to make solution of many different compositions, right? The different composition, yes, solution we can make the different compositions. Solutions are almost always transparent. Solid solutions are an exceptions. For example, because the solutions means basically the solute get dissolved. Okay, solute get dissolved means that solute is spread out on the vicinity of your solvent. That's why it's spread out and it breaks down and it leave in due to the intermolecular forces. So it is a transparent. So solute dissolved there. However, the solute is there, but for example, if you think about the sodium chloride, right? Let's see what happens in the sodium chloride. If you put the sodium chloride on the, suppose this is the water and this is sodium chloride, this is sodium chloride, and sodium chloride will be sodium plus and chlorine minus. So sodium plus and chlorine minus. Sodium plus will be surrounded by about 4 or 5 water, 1, 2, 3, 4, 5 water, 6 water, okay, and chlorine also surrounded by 1, 2, 3, 4, 5, 6 water, right? It lives like that. So okay, so look at that. This is here, that is, they are surrounded by this. So You cannot separate this by filtration. So sodium become far away from the chlorine. So sodium atom is very tiny, right? Atom is the angstrom scale. That's why we cannot visualize that by eye, because all the lattice breaks down. Sometimes molecules, if the ionic solution, so if it is the solute is the ionic, then the molecules separate into two parts. However, they are there, total balance charge is 0. Sodium chloride, sodium plus this chlorine minus, other sodium plus other chlorine minus, they live like that. This is the ionic solution, because this is the solute is the ionic. But at least the lattice break down. If this is not ionic, then lattice only break down, and all the molecules separately live together. For example, if you think about the sugar solution, right? And all sugar molecules are in water, okay? And these sugar molecules are separated from each other because of the dissolution, right? When you solvate something, the lattice break down, and when you have a lattice is the macromolecular, lattice is the macro form. It is a larger form, bulk form. You can view that by your eye, millimeter, centimeter, that much big crystal is. That's why you can see that. But once you dissolve that in the water, every molecule gets separate, and these molecules float inside the water. I mean, that's why one molecule is very, very small. One molecule is about angstrom size, and our eye cannot see that angstrom size small molecule, right? So our eye are not made to actually see that. Our tongue can taste that sugary taste, right? Tongue has the sensors, molecular sensors. That's why these sensors actually find that it has sugar, but the eye cannot, because it is beyond the visible range. It's a size of the molecule is beyond the visible range. That's why our eyes are made for the visible range, that is the 300 to about 700 nanometer, right? So in that visible range, so visible spectrum range, our eyes are made for that. So our eyes cannot see beyond the visible range. X-ray, microwaves, no, our eyes cannot see that, right? So that's the reason we cannot see those molecules which get dissolved in the water, because they separate. So for example, previously these are the sugar molecules. These are the sugar molecules. This is one molecule. Okay, this is another molecule. This is another molecule. They live together and forms one crystal, right? They live together, forms the crystal. That's why we see that crystal things, right? But once it gets dissolved, they all become separate. They all become separate. And this one single molecule is angstrom scale. That's very small. Its length is beyond the visible range. That's why we cannot see that. Okay, so that's why we cannot see that. So that's the reason solutions are almost transparent. Solution can be separated into pure components. Okay, so the separation is physical change, not a chemical change. If you can separate that, right? But that separation is, you can separate a solute and solvent, but that separation is not the chemical change. That is the physical change. Okay, that's the physical change. So these are the characteristics of the solution. Now let's go back to the solubility. So solubility means, now let's take one example again. Solubility. Okay, so solubility. So to understand solubility, let's do one experiment. This is my beaker, and a beaker has water. Let's say water, 100 ml water. This is 100 ml. Okay, now let's say start dropping down the salt here. If you drop the salt at first, it gets dissolved, 10 gram. Let's say at 1 gram more, it also can get dissolved. 1 gram more can get dissolved. Okay, so let's say 35 gram get dissolved. Let's say 36.1 gram, some sodium chloride deposit back here. So this 100 ml water only can solve it, for example, about 36 gram. Okay, if you add more than 36 gram, it stops make solution. Okay, so that's why it cannot dissolve more. That's why solvent has fixed capacity to dissolve it. So maximum amount of a solute can be dissolved in the solvent at a particular temperature, that maximum amount is said to be the solubility. And in that type of the solution is said to be the saturated solution, means it is saturated, you cannot dissolve further. Okay, so that's why solubility, first of all, to understand the solubility, understand the saturated solution. Saturated solution. Saturated solution is that solution at which we have dissolved the maximum amount and we cannot dissolve further. That is the saturated solution. And the concentration at that saturated solution is the solubility, or the maximum amount that can be dissolved in the solvent is said to be the solubility. So that property is the solubility. The maximum amount of the solute that dissolve in a given amount of the solvent at a given temperature, right guys? It depends upon the temperature also, and that is said to be the solubility. Okay, so solubility is a physical constant. It is just a constant, right? It is a value, so how much we can dissolve at a particular temperature. So each solid has a different solubility in every liquid. So one liquid has different solubility. For example, sodium chloride, you have a 36 gram in water, but not the 36 gram in oil. It is a different. Not the 36 gram in the, for example, in the alcohol. It's a different, right? So different solubility in different solvent at a different temperature. 100 degrees centigrade, you have different solubility. 200 degrees centigrade, you have different solubility. So solubility also different. Okay. So now some liquids are insoluble in each other, as for example gasoline and water. You cannot dissolve them. That's why like dissolve like. So every liquids cannot dissolve every liquids. Okay. So like dissolve like. So there are two types of the solvent. One is said to be the hydrophilic, and other is the hydrophobic. Hydrophilic means water loving, or that can dissolve in, can mix in water and can make either H bond or can dissociate. So that's the hydrophilic. Other is the hydrophobic. Hydrophobic means water hating, or that cannot dissolve in water. Only the force of attraction is dispersion force, is basically force and is basically repulsive. Okay, that's why hydrophilic means water loving. It can dissolve in water or it can mix in water, but the hydrophobic cannot mix in water. For example, oil is hydrophobic. Okay, oil is hydrophobic, it cannot mix in water. Okay, so hydrophobic, for example hydrophilic that can dissolve in water. For example, ions, let's suppose that. Okay, that's the hydrophilic. Alcohol, for example, that also can be mixed in water, right? Because alcohol has what? One OH bond. If you remember that one hydrogen bond alcohol can make, right? CH3, CH2, OH, let's say. So O oxygen, this is the OH, and this OH can make the hydrogen bond with the water. That's why it can mix in water. So this is the hydrophilic. And hydrophobic, for example, oil. For example, alkane, CH3, CH2, CH2, CH3. Butane, for example. You cannot mix that in water. Okay, because it is the oil, because it don't have any hydrogen. Look at that, hydrogen has, water has H2O, right? It can make the hydrogen bond, but it can't make the hydrogen bond. So that's why this guy cannot mix in water. So you can have the two different component of that mixture if you dissolve this hydrophobic and hydrophilic. Hydrophobic and hydrophilic are basically repulsive. So if you mix these two, you can easily form one layer of the hydrophilic, that's the water, and other layer of the oil. You can have that. Okay, so that's why hydrophobic, that basically it hates the water, it's repulsive with the water. So that's why if you mix these two, you can easily have one water layer and other oil layer, both are separated. Okay, so that's why, because this has the less density, that's why it can float on the surface of the water. So other liquids have the limited solubility in each other, as for example ether in water. Ether has solubility but 6 gram in 100 gram of water. It's not like the sodium chloride. Okay, still other liquids are completely soluble in each other, for example ethanol and water, because ethanol is the hydrophilic. It has ethanol, oxygen, OH group there. OH can make the hydrogen bond, right? Hydrogen bond is that hydrogen which is attached with oxygen can make the hydrogen bond with the either oxygen or fluorine or nitrogen, and that's why, and hydrogen should be attached with either oxygen or nitrogen or fluorine, and it can make the hydrogen bond with then nitrogen, oxygen and fluorine of the other molecules. So we have studied that in the last chapter, hydrogen bond. Okay, so now let's go further. The solubility. Saturated solution, a solution in which the solvent contains the maximum amount of the solute, right? After that we cannot dissolve. We already discussed that. What is the saturated solution? So if you think about the saturated solution means, so I give you the one example. Okay, you add the sodium chloride, it will dissolve. Add again, it will dissolve. Add again, it will dissolve. But a situation comes at which if you further add the sodium chloride again, if you put the additional sodium chloride, then that additional sodium chloride will sit down here. It will get precipitate here. So it cannot dissolve as much as you want. It can dissolve the maximum fixed amount of that, right? In 100 ml of the water, maybe 36 gram you can only dissolve, and not more than that. So 37th gram will be sit down in the bottom. So that is solution is the saturated solution. So the maximum amount dissolved, the solution in which the maximum amount of is the dissolved, that solution is the saturated solution, and that is also condition set to be the equilibrium. So unsaturated solution means it is not saturated, still you can add more. And a supersaturated solution means beyond the saturated solution. Saturated solution means that the equilibrium condition. Okay, if you add more, it will give you precipitate. If you eject, it can add more. So that's why this is the equilibrium condition. But the supersaturated means beyond the saturation. So you get the saturation point. If you add further, then the supersaturated means you can have the crystal at the bottom. Okay, a solution that contains more than the equilibrium amount of the solute that can be dissolved at a given temperature. When a supersaturated solution is destructed in any way, the excess solute separates and the equilibrium solubility. Okay, so far we have studied the solution, definition of the solution, types of solution, right, and the properties of the characteristics of the solution. And this the next video we will discuss on the factor affecting the solubility, like the temperature, pressure, what happens to the different salt solution or gas, what happens to the gas, and lots of other things we will study in the next video. Aristotle. See some factors